the sphere has some radius r, bring it close to a surface, which is typical thing that you do in experiments, and do some analysis for what the forces could be. And let's focus on the quantum case. So what I would say is that if I have a Casimir force operating between these two, it is going to be proportional to h bar c. It is going to be proportional to the polarizability, which scales like the volume. And the only other length scale that can make this combination into a force is the separation h. And since this thing has 4 powers of distance over force, over energy, and we want to make it into a force, I need 5 powers over here. Okay? So that limit is pretty much well understood. Now suppose we bring it close, and this is actually the situation that you have in most experiments, where the sphere is so close to the surface that effectively I should be measuring distances not from the center of the sphere, but from the distance of closest approach. And since these kinds of forces fall off very rapidly with separation, you would say that the region that contributes most to the force is the one that is closest to the surface. So that's observation that for sufficiently rapidly diverging forces, you are dominated by the closest proximity, allows you to calculate things in a quite general body of forces by what is called the proximity force approximation. What that proximity force approximation amounts to is to imagine that essentially your surface, could be sphere or could be anything, is composed of a bunch of parallel plates whose separation varies as you go away from the closest approach. But what you do is you sort of add up forces that you would have for parallel plates. And for example, if you do that, you end up with a force that is 2 pi. If the radius of this thing is r, it's r, and the parallel plate energy per unit area. As a function of h. And the parallel plate energy, again, we can sort of calculate based on these dimensional analysis. We even calculated what the coefficient of that was. And so this is really the approach that was used in matching the result of the experiments to what was known from the calculation of Casimir, although they were using something that was a sphere rather than parallel plates. The thing is that up to about 5 or 6 years ago, while one can show that this is asymptotically correct as h goes to 0, exactly what asymptotically correct didn't have much sense, because you didn't know the systematic corrections to this formula. So very recently we were able to calculate what these systematic corrections are, and essentially they turn out to be a series in the curvature of the object on its point of closest approach. But let's not go into that, and instead sort of continue with this general dimensional analysis and try to figure out what the interaction of not a sphere but a cylinder that is held parallel to a plate is going to look like. So I'm going to tell you that this has radius r. It is at some separation from its center to the plate that I'm going to call h. And okay, in principle, I'm going to assume that this is much larger than all of the other dimensions that we have. So we have a long wire that we bring close to the surface. So this is a quiz. I'd like you to guess which of the following is likely to be correct. So there are various ways that I can approximate the result. All of them, let's focus on the energy as a function of h, so that the thing that I want to write down on the other side should have dimensions of energy. And I'm only going to think about the quantum case, so I will put the h bar c that has to be there. One thing that is immediately obvious is that whatever answer that I should write down should be proportional to the length. The same way that the energy for parallel plates was extensive, was proportional to area, the energy here is going to be proportional to L. So once I know the overall dependence over here, I can make it up by putting appropriate powers of h over here. So one guess is that what I need to do is to imagine I have lots and lots of small spheres and add up their interactions to the surface. So this is what I would call a pairwise approximation. So basically you say, oh, I know the interaction of each atom or molecule or volume element to what you have over here. You integrate over all of them. Not surprisingly, the answer is going to come up to be proportional to the volume over which that you are integrating. And so what do I need? For an energy, I need one more power compared to that, so I need h to the fourth. So that's proposal number one. I'm writing energy as opposed to force. Okay? Okay, now let's try something else. Let's sort of go with the idea of this proximity. So one very simple thing that I can do is I can say, oh, this is kind of from the perspective of this thing that is looking up. You see something like a ribbon, and the energy of a ribbon is proportional to the surface area that I see. So I will write LR, which would then make this h cubed. There is actually a better way to do it, which is to do exactly the same thing here and integrate over all surface elements that are in parallel. So if I do that, which is this proximity force approximation that I have over here, then that will lead to h bar c. Because of the integration that you have to do, well, first of all, if it's close enough, you have to distinguish between h and h minus r, and you will get here something that goes like h r to the 1/2, and then I have to make it up by putting a 5/2 here. Okay. So anyone believes these? So none of these is correct. Once you do the calculation, yes, it should be L. All of them should be proportional to L. Okay? So the correct one is you would have said, oh, it has to be proportional to length. Then I have to make it up by 2 powers of h. Okay, that's correct. You say, well, what happened to r? As r goes to 0, this answer should go to 0. Well, power counting is correct, but you will get something like a log of r over h down here. And the reason for that is essentially you have to think about what is the most important fluctuations that are contributing to the interaction. And this is kind of like an antenna. So you're going to have these long wavelength current fluctuations over here. And these long wavelength current fluctuations, any of you who did electromagnetism from 2 wires, you know that logarithms appear all over the place. So that's the correct answer that shows up. Just to tell you that dimensional analysis works, but you have to be careful in cases such as this, and where you have more general objects, and maybe I'll show you some transparencies about how to deal with more general objects. But really the key to our difficulty here of dimensional analysis is that we have multiple length scales in the problem. This R has to sort of be compared to L and H, etc. So there is a way to get rid of that and give exact results as far as dimensional analysis is concerned on set of objects that I will call scale invariant shapes. There are a bunch of them. I'll really focus on two of them, and you can think of all the others. Suppose that I bring close to this plate not a sphere, but a cone. Okay, so this distance from the tip is h. Okay, then there is really no other length scale in the problem except h. There is no radius. This thing in principle extends all the way to infinity. So for this object, I know for sure that actually let me just write down the let's write down the force. In the quantum case, it has to be h bar c divided by h squared with some coefficient that I don't know. In the classical thermally dominated regime, it has to be the usual formula that we have seen a number of times. Kt over h is the thing that has dimensions of force. Okay, so the thing is that in some cases we can actually calculate these things exactly, and we saw the case, let's say, where there was a coefficient 1/2 that was universal. In both of these cases, there is also a universal coefficient, but that universal coefficient now actually depends on what the opening angle of this cone is. So essentially, they are geometric entities that are still universal. Okay? And similarly, there will be a corresponding one for the quantum case. And you can imagine that, let's say, if the cone has not approached at the 90-degree angle that I have indicated, but potentially slanted, then there could be also a dependence on not only theta, but also the angle phi. Okay? So we will calculate some of these universal amplitudes, but I'll do them in a much simpler case to give you another set of ideas in the context of polymers. Another type of scale invariant shape that you can imagine is to bring a knife edge, or if you like, rather than a knife edge, maybe something that has an opening angle, a wedge. Okay? So you bring a wedge, again, you could have some kind of an opening angle theta, keep it parallel to the surface, bring it for a distance h, then you expect in these cases indeed something very much like what I wrote over there. It should be proportional to whatever this length is, because I expect that on the basis of extensivity. So force will have an h cubed, and amplitude that depends on opening angle, corresponding one for the thermal case. So the key, what I wanted to mention, is that that problem was difficult because you had length scales, and I can make things simpler and more universal by removing length scales as much as possible. So I removed length scales associated with geometry. But remember when we were having these discussions of Casimir retarded van der Waals, etc. forces, there were potentially length scales that would emerge from resonances of the material. So again, this kind of results are only correct if the material itself does not present additional length scales. Okay? So the thing that I'm going to calculate these coefficients for, yes? Excellent. So let me answer that question specifically for the next problem that I was going to tell you. Okay. So the problem for which I want to calculate this, and more specifically the thermal version, is when this expression arises in something that was actually shown this morning, where this potentially could be the tip of an atomic force microscope, to the top of which you have attached some kind of a polymer, and my polymer does not have any internal structure made of amino acids or whatever, so I don't worry about energy factors, it's only entropic factors. So this polymer fluctuates, and as long as this probe is far away, there is no constraint on the fluctuations. As I bring the probe close to the surface, there is less room for the polymer to move around, its entropy is reduced, and there is an entropic repulsion that you would expect. Now, the answer to the question that you asked is, well, what about the finite size of this and the fact that it doesn't extend all the way to infinity? Well, typically we don't have polymers that extend to infinity either. So this problem has some characteristic length scales. Let's say there is a monomer size A, the components that make up this polymer. There is some overall size because this polymer is made up of a finite, although very, very large number of monomers. There is a kind of typical radius of gyration. Let's call that Rg. And now I have this additional length scale h. Okay. So let's see when this relation should be valid. Well, I want this microscopic length to be irrelevant. So I'm probing things at length scales that are much larger than the atomic spacing. But I want to see the effect of this polymer being squeezed out. So I want to be at distances that are much less than the typical Rg. And for my whole argument of scale invariance to work out, this Rg must be much less than whatever the characteristic size of the probe is. Okay, does that answer your question? Okay. And you can do a similar thing over here. Okay. So let's build towards calculating what this entropic repulsion from the polymer is going to be. Okay, let's start with some preliminaries about polymers. There's various levels of approximation that one can make, and I can go through them, but for the purposes of this lecture, let's assume that you agree with lots and lots of approximations so that for purposes of the qualitative things that we want to look at, essentially I'm looking at a random walk. Okay? So if I start from some origin, doesn't matter where, and I take a random walk that has step size A, and I take n such steps, after n such steps, I end up at some vector r from the origin, which is clearly the sum of the random steps that I took. So r is sum over alpha running from 1 to n, whatever step I took at the nth level. And if I'm an unbiased type of thing, the average of r is 0. The average of r squared is proportional to n a squared. I'll come back to a coefficient here, because what I want to do is to say that also I'm adding lots and lots of random variables. So furthermore, I know something about the probability distribution. But let me cast this slightly differently. Let's say that I don't worry about where I end up, and I ask what is the partition function of this system after I take n independent walks. Well, if you do it on a lattice, it will be, let's say, on a square lattice, you have 3 steps, 4 steps, or whatever. There is a constant that you have to raise to the power of n, which is some extensive part of the free energy of this thing if I were to take the log. But let me constrain it to end up at location r. Then essentially what is left is the probability that among all possible endpoints I ended up at r. So I have to reduce this, and this is reduced because I'm doing a sum of random variables to have the form of a Gaussian. And I will write the coefficient of the Gaussian in this fashion, 2n a squared, and I have to normalize it in 3 dimensions, so it will be something like this. And the reason I hesitated a little bit about writing the coefficient here, rather than taking steps that are unit length, I take steps that are equally minus plus a in x, y, and z direction, because this is really x squared plus y squared plus z squared. Each one of them averages this, so I really have a trivial factor of 3 to put there. Okay? So that's this. No, this is r. So this r squared here is x squared plus y squared plus z squared. So this is really a probability distribution in 3 variables. It's a joint probability distribution. Okay? Now this is the form of fluctuation-induced force that we teach in first physics classes, because we say that this is like an entropic elasticity. This probability distribution looks like I have some kind of a Hookean spring that connects the endpoint to the origin. And if I had a Hookean spring, the probability would have been the strength of the energy of stretching a Hookean spring, which is proportional to r squared and over 2. So that would be the energy. If I'm at temperature T, you would put a kT here. And by matching these 2 expressions, you can see that the effect of the entropy is to essentially give a contribution to elasticity of this, which is kT divided by na squared, which is the same thing as kT divided by r squared over 3. Okay? So, okay, so we knew this formula of entropic elasticity from way back there, and this is one example, really the first example that you probably saw of a fluctuation-induced force or interaction. Yes? Okay, so this is a partition function. So if I start and let's say perform a random walk on a lattice, the first, let's say in 3 dimensions on a cubic lattice, our first step is one of 6 places, the next one is 6 places, so this would be 6. Okay, but who knows whether you put energy, etc. Ultimately, you will have an exponential dependence because of extensivity, because log of this object has to be extensive. This is the same thing that we usually ignore, right? This is the same infinity. Okay? And you can see why it can be ignored, right? It doesn't contribute to entropic elasticity. Okay? Now, the reason I went through this, because I need the following. That this quantity, z as a function of n and this vector r, clearly satisfies the diffusion equation. And I'm going to essentially ignore the contribution due to c, because I know at the end of the day it's not going to be important. If you want, you can add a term cz here or something. Doesn't matter. Okay? Because for all of the things that are interesting, I really need to solve the diffusion equation with n replacing the roll of time. Okay, so what's the first thing that I wanted to do was to go and redo the Casimir calculation. And by Casimir, I mean only that I use the setup of 2 parallel plates that we typically associate with calculating Casimir forces. Okay? And what I do is I put a very, very long polymer here. I'm just repeating something that is in all kinds of textbooks, just to sort of get us going on use of these approaches. So once I have confined this very long polymer to some distance h, then I have removed a lot of fluctuations that it would have liked to have, so it is unhappy and it is exerting some kind of a force on these 2 surfaces. In dimensional grounds, hopefully you can all figure out exactly what the dependence on h and everything is, but I can actually calculate the coefficient in this case using the diffusion equation. Just hold on a second, we don't want this to keep going. Okay, so what I need to do is essentially solve the diffusion equation, and it is going to not depend on the xy coordinate. It's confined along the z direction, so the answer really is going to be d2 by dz squared times the partition function. And actually I should have made sure that I get all of my dimensionalities correct. I had introduced an a squared here, and really in order to get that answer back, I have to introduce a diffusion coefficient of a squared. Okay? So let's imagine that we have a very, very long polymer. Then this behavior of differential operator is going to be dominated by the eigenstate of this Laplacian that has the lowest or largest or most important eigenvalue. And that is obtained by looking at the state that is proportional to sine of pi z over h, so that it vanishes at 0 and at h. Okay? So that's the appropriate eigenstate, the sort of the probability of the endpoint is going to kind of look like this. If I were to put this over here on the right-hand side, I will get pi squared over h squared that multiplies by a squared. So I immediately see that the n dependence is going to be pi squared a squared over h squared n. Okay. In principle, if I wanted, I could have added this c to the n, but it doesn't really make much difference. It has no h dependence to it. Okay? So then, as usual, beta times pressure, you've seen this many times, is d log z by the volume. So I have d log z, which is dependent on h, with respect to volume, which is a times h. Yes. Should be minus in the exponent. Right. Okay. So what does this give me? It is 1 over a d by dh of log of this is going to be minus pi squared a squared n over h squared. So this is going to give me n over a pi squared a squared over h cubed. What sign? Okay, the sine function is not extensive in n, right? So I could, in principle, put that, but then it will be in the limit of large n, it would fall off. But you're right. In principle, I should include that. Okay? So we find the usual result that, say, Dejean has, and there is a very nice blob picture for explaining why this result is. But in any case, we can calculate what the effect of this constraint is in generating some kind of a force per unit area. You can see it is proportional to the density of the monomers and falls off as 1 over h cubed, and the thermal coefficient kT is over here. Now, one other thing that I want you to sort of note is that close to the either one of the surfaces, it doesn't matter which one, close to the obstacle, let's call it, the partition function, because of these sign factors that I have over here, has a dependence that goes like z, more precisely z over h, but doesn't matter. It's just that it goes with the first power. It vanishes linearly. Now that linearly, you say, well, it has to vanish, it vanishes linearly. Actually, no, it vanishes linearly because of this being a regular type of polymer. Sorry, not a regular polymer, but a random walk. You probably know that in this case, what we have is that the typical fluctuations go like square root of n. If I were to include self-avoiding interactions, just for later reference, then typical fluctuations would go like n to some different exponent nu, where nu is approximately 0.59 in d equals to 3. And once you sort of start playing around with these various exponents and all of that, this kind of linear behavior, etc., will also be modified. Now, I'm going to derive that linear behavior through another approach. Which is the following. So let's imagine that I have just one plane that the polymer cannot penetrate, and I start my polymer at a microscopic distance, let's call it A, from this surface, and ask what is the density for the end point. Okay? So essentially, I have to solve z of z subject to z of 0 is 0. I don't want it to go down there. And it has to be the solution to this equation. dz by dn is a squared d2. Well, I can write down all of the other coordinates, but the answer will not really be interesting in the other coordinates, but let's put it there anyway. Laplacian of z. My claim is that if I take the solution that I had before, which was e to the minus r squared, which was x squared plus y squared plus z squared divided by 2na squared, divided by 2 pi n a squared to the 3/2, and take a derivative of it with respect to z and multiply by a, then I will get the correct answer in the case of this plane. And typically, the way that you usually arrive at that result, if you haven't seen it before, is to use method of images. You say that I know how to calculate all of the walks, and that's going to be the answer. I'm going to subtract all of the walks that at some point crossed the origin and then came to this point, because those walks had a reflection that started at a reflected point. And I subtract all of those image walks that I start at the image point. And so then I have to subtract that and that. So I have to take a derivative, multiply by how far I have gone. Also, you can check that once I take this object and take its derivative, the derivative with respect to z will generate a term that is proportional to a and a z divided by na squared, and then the rest of the exponential and all of that. And that clearly has the right property that when z goes to 0, it goes to 0. And furthermore, confirms this linear result that I had mentioned was happening over there. Okay? So more generally, what we find is that when we have these obstacles, the density of the endpoint calculated by this analysis is going to vanish when I approach the obstacle. And you can imagine that that's going to be true if I start close to ask how likely it is that the endpoint of this polymer is a distance r from the tip of the cone. Okay? So given this kind of analysis that we now know, you expect that there is a depletion factor. So as I approach r equals to 0, that density should go to 0. And it turns out that it doesn't go to 0 with linear behavior, but with a non-trivial exponent that depends on the opening angle. And again, this is something that you may have seen in electrostatics, because you end up having to solve the same Laplacian operator near a cone, and you probably have seen that the strength of the electric field, for example, has a non-trivial dependent on the angle. So all of these things ultimately are really because you have to solve the Laplacian equation. Okay? Now, why is it that I'm spending time talking about this depletion factors and all of that? Because it turns out that in order to calculate this amplitude, etc., I don't have to repeat the calculation that I had over there, solving the Laplacian in the geometry of a cone separated by a plane at the distance h. Probably it's possible. I really don't know, because it's a complicated problem with additional length scales and all of that. Fortunately, I don't need to do that for the following simple argument. So I have convinced you, hopefully, that the force acting on the polymer when it is at a distance h, just on dimensional grounds, has to be of a form kt over h, because that's the only length scale in the story in the appropriate regime that I have told you, except that there is an amplitude that I know that doesn't depend on, that depends on this opening angle. I say, okay, fine. Let me do the following. Let me bring the polymer when the cone and the polymer that is attached to it are very, very far away, so that there is no touching. And then I bring it all the way so that it touches the plane. And I ask, how much work did I do? Okay? So the amount of work is going to be the integral of force times separation. So I have f of h dh. And the appropriate distances, I can go from one distance to another. Certainly, the shortest distance that I can approach that makes any sense is of the order of monomer size. The largest distance that I can think of before the force goes to 0, and I don't have to worry about this thing, is something that is of the order of some radius of gyration, the kind of thing that we defined before. Okay, so this is an integral a to r of dh kt h with a. Okay, so I've just reproduced what a is, f is. So I have kt a. These are constants I take outside. Then I have the integral of dh over h. I can do that. It's log of r over a. Now, I told you that quite generally for polymers, much beyond what these approximations that I have been using, if I have a sufficiently long polymer, its length is going to be something like an to the nu. So I know that the amount of work I have to do in pulling this polymer from touching the surface with the cone all the way to where it doesn't feel anything is related to nu log n. Okay? Now, the amount of work is also the difference between the free energies. So free energy is minus kt log of z, and the difference in free energy, I have to take the log of the z when the cone is touching the surface, minus log of z when the cone is very, very far away from the surface. Okay? There was one thing that I neglected to tell you that, okay. If I were to take the result that is on the board and ask what is the partition function of the polymer in which I don't care where the endpoint is. So if I don't care where the endpoint is, I have to integrate over z, I have to integrate over x and integrate over y of this zp. And since this object is d by dz, I can immediately do the z integration. I end up with a Gaussian, except that through the processes of various derivatives, etc., that I have to do, I end up, because when I do this, I bring down a factor of n. You go and calculate all of the results, and you find that you pick up a factor of root 2 pi n. Okay. And what that square root of n describes is the reduction in entropy that you have suffered because you are close to this plate. So essentially, when the polymer is far away by itself, we said that it behaves like this constant, I don't know what I call it, c to the n. When I bring it close to the surface, essentially, the fact that it cannot explore half of the space reduces this c to the n to c to the n with this square root of n. Okay? So there is all of these constraints, again, giving you reductions in the partition function in the probability, and this is one way of calculating what that is. Now, quite generally, I introduced the exponent nu for polymers. There is another exponent that people in polymer physics use, which is that the number of configurations, or the free energy or the partition function, the partition function always has this exponential factor, but potentially, like here, it has a power of n, which is indicated through exponent gamma. Okay. So what we have shown is that in space, where the polymer sees no constraint, there is no factor of n. So by convention, that corresponds to gamma being gamma 0 is equal to 1. Whereas if I constrain it to start near a plate, because I cannot explore half of the space, it's not really that big a constraint. The whole thing still goes exponentially, but there is a subleading power of n that encodes the cost of not being able to go down there, which makes the gamma, let's call it the gamma of a plane, to be 1/2. So that what we have here is 1/2 minus 1, which is this n to the 1/2. It's just the notation of how gamma is defined. Okay? And similarly, if I were to do the calculation of the constraint of starting the polymer not on the plate, but over here next to the cone, there is a gamma that is associated with that geometry. Okay? So what I claim is that this partition function, you have the polymer over here, is c to the n, n to the power of the gamma that corresponds to the cone minus 1. Whereas this corresponds to c to the n, n to the power of a gamma that corresponds to a cone touching a plate that I'm going to denote by gamma cp minus 1. Okay? Now you can see that when I subtract these two partition functions to calculate the free energy difference, this non-universal part does not come into play. And what I will get is essentially something like kt log, okay. So essentially I will get gamma cp minus 1 log n minus gamma c minus 1 log n. So I will get log n gamma that corresponds to c minus gamma that corresponds to cp. Okay. So I have now two results. Both of them give me the cost of moving this polymer from touching this plate to being far away. And so the two of them have to agree. The work should be the difference in free energies. Both of them, you can see, have this log n behavior. So immediately I can identify that this amplitude is simply the difference of the two gammas divided by nu. Okay? This is generally true, although I did various calculations for random walks. For any complicated polymer where all of these exponents are non-trivial, the force amplitude can be related by this. So once more, going back to this theme that we had, that when we have these universal relationships, you can figure out everything except the amplitude by dimensional arguments. The amplitude, which is universal, has some character which is like a critical exponent. Okay? So I don't really need to calculate this geometry. I just need to focus on the self-similar geometries where I have a cone by itself and a polymer next to it, or the cone touching the polymer. Actually, I said all of these things for the case of the cone, but they are true for any scale invariant object. And in particular, if I had my polymer attached to the one point on this wedge, and then it was executing some kind of a behavior such as this, I would have stated all of these things exactly, except that the two configurations that I have as limiting behavior are when the polymer is attached to the wedge far away and when the wedge is touching the plate and the polymer is part of that. And I'm just for simplicity going to evaluate for you the exponents in this case, because in this case the cross section is clearly two-dimensional, and so all I need to do is to solve the problem of something like a Laplacian in 2 dimensions, where I have some angle theta at which the solution to my Laplacian has to come to 0. Yes? The capital A here is actually the sign that corresponds to a repulsion. Okay? So in this case, what is happening physically is that the polymer generally wants to fluctuate, and if I push it down, it has less room to fluctuate, so it's unhappy. It says my entropy has gone down. It wants to push back. So for the cases that I have mentioned over here, this capital A is in the repulsive direction. Now, in about half an hour, I will give you an example where it actually can become attractive, where the surface itself, rather than being repulsive, may be attractive. Okay? All right. So in general, for something like a cone or even the wedge, with some appropriate symmetry, I have to write the Laplacian operator in the appropriate coordinates that involve, let's say, a radial part and some kind of an angular azimuthal part, theta. So small theta is the distance along this solid polar direction. Big theta, I hope I have made sufficiently clear, corresponds to the opening angle of the cone. Okay, then the Laplacian operator in general becomes something like 1 over r squared d by d theta squared, I should write it. Okay. So the Laplacian that corresponds to generalized cones with a symmetry where you have a radial and a polar coordinate only. In the radial part, you have r to the d minus 1, d by dr, r to the d minus 1, d by dr. So that acts on the radial part. And then there is a component that acts on the angular part, which is 1 over r to the d minus 1, d by, 1 over r squared, sine of the angle theta to the power of d minus 2, d by d theta of sine of theta to the power of d minus 2 d by d theta. Okay, so all of this will act on whatever function you have. Now, the kind of functions that I expect to have that are relevant are things that vanish as r goes to 0 with one of these depletion exponents. So as p goes to 0, it has to vanish. And then there is some function that depends on the angle, theta. Okay. Now I expect the boundary condition to be that psi, when small theta is big theta, is 0, so that I don't have anything on the cone. As I said, I'm going to just look at the case d equals to 2, so that I don't have to look at generalized Legendre functions, etc. And what I will have, actually no, before doing that, if I were to substitute this form into this equation, then the r dependence I can get rid of, and I end up with an eigen value equation for the angular part. So I will have, so this is big psi of r and theta. The small psi is going to satisfy the equation sine to the power of d minus 2 theta, d by d theta, sine to the power of d minus 2, d small psi by d theta. And this is important, that if I look at various derivatives with respect to r that appear, they are going to act on this. So they bring down powers of p and involving this. And so this becomes p d minus 2 plus p psi equals to 0. So I can impose this kind of a form with an exponent for this depletion p that I don't know of. And then I find that that p will appear as an eigenvalue of this equation where psi has to satisfy this boundary condition. Okay? Now, and clearly in the case of d equals to 2, this equation simplifies very dramatically and becomes the second derivative of the angular function plus p squared psi should be 0. Okay. So that's for something that we can immediately solve. So over here, the solution is going to be something like psi of theta should be proportional to a sine function, so that when small theta becomes big theta, it goes to 0. So I write t minus small theta minus big theta. Now my other constraint here, I have to be careful, is that by symmetry, I expect that by the time I have hit pi, I can continue with the solution that is coming from the other side. So the derivative psi prime at pi over 2, at pi should be 0. Okay? So the derivative will bring the cosine. So what I do is I write here pi minus big theta, and the cosine of pi, let's again make sure I get this right, over 2. Okay. So I have created a solution that when small theta is big theta, it goes to 0. That's fine. The derivative function is going to be the cosine of the same thing. When theta equals to pi, then I am calculating cosine of pi over 2, which is 0. Okay? But that immediately, if I were to put it over here, tells me what P is. So we get that P for the case of the cone is pi 2 pi minus theta. Okay? So essentially, the way that the polymer depletes on approaching the angle of the apex of the cone is parameterized by this p-value. And this p-value depends on the angle theta. It's pretty much like what you would have for the electric field close to tip of a cone. Now for the case of the other case that I need to look at, which is when the cone is touching the plate, the boundary conditions that I have is that psi not only at big theta is 0, but at pi over 2 is also at 0. Okay? And then the solution is sine of big theta minus small theta, small theta minus big theta as before, so that when small theta becomes big theta, you go to 0. When I hit pi over 2, I want it to be 0, so I put here a pi over 2 minus theta 0. So when this is pi over 2, this becomes 1. I put a pi here, so it becomes sine of pi and it goes to 0. So we find that according to this, P of the cone plate is pi divided by pi over 2 minus theta, which I can write as in this form. This is big theta. Okay. Now, there is one other relationship. There is an exponent identity. You can see that somehow the exponent gamma that I got here, I obtained by integrating over all configuration of this object. And the fact that I got the square root of n was very much dependent on the way that the depletion occurred on approaching the surface. So you won't be surprised if the exponent gamma is, for a particular geometry, is very much related to the depletion exponent that I've called for that geometry. In view of time, I won't go into that. It turns out that gamma is something like 1, gamma minus 1 is something like p nu, so that actually this difference is the same as the difference of the two p's that we mentioned, pc minus pcp. So using this and the information that I have over there, I can figure out immediately, and sorry that I go down here, what the amplitude is going to be for bringing a wedge close to the surface. It is simply the difference between these two things that we've calculated. And if you do the algebra, it comes out to be something that is as follows. 3 pi squared divided by 2 pi minus big theta pi minus 2 big theta. Okay. Sorry about this component. I put in too much, probably, algebra. It wasn't really necessary. So let's go back and think about the concepts that are important. Yes? P is not the same thing as gamma. There is an exponent identity between gamma and P. Okay, so in critical phenomena, gammas are typically indicated as exponents for susceptibilities, if you have remembered your critical phenomena. And susceptibilities can be obtained by integrating correlation functions. So there is an exponent identity that appears as gamma is 2 minus eta times nu or something. Okay? So this eta is actually this P. I should have called it eta from the beginning, because it determines correlations between one point and another point. So up to a factor of nu, which is fortunately cancelled out here, you can relate the difference of 2 gammas to the difference of 2 etas, which is the same thing as the difference of 2 p's. So there is a little bit of exponent identity algebra that I skipped over, because it's not particularly relevant. So the story is the following, that just on the basis of dimensional analysis, we can figure out that the force should have this form of kT over h with some amplitude. Now that amplitude is somehow related to various other critical phenomena, critical exponents, and this simple analysis of looking at the work to move the polymer away or the difference in free energies gives a relationship between the force amplitude and some exponents that are relevant to the polymer. This is quite generally valid. Now, what do these exponents measure? The gamma exponent or the P exponent, they really tell you that when you bring a polymer close to a scale invariant object, the number of configurations has to be reduced. The extensive part doesn't get reduced. It is the sub-extensive n-dependent part that gets modified. And that's a universal aspect. There is no cutoff, etc., that is appearing in the way that these exponents are defined. So what we need to do is to calculate what these gammas are. Now, one case where we can more or less simply calculate them is for idealized polymers that satisfy this equation. And even then, you can see that having geometry such as the cone or the wedge involves solving, in general, complicated but not impossible eigenvalue problems to get what these depletion exponents, hence the gamma exponents are, and hence what the overall force amplitude is. So that's the general philosophy of why they are universal. Now, of course, if I want to calculate the same thing for the case of the Casimir force, the story becomes much more complicated. There are more difficult things to calculate, etc. So, yes. Yes? Well, that is encoded in P, right? So the question that you are asking is how much uh, uh, reduction in entropy you have. And one way of measuring that reduction in entropy is in terms of how many n's you have lost. Now, the exponent nu, that was your question, right? Why doesn't nu appear? Really, measuring things either in terms of the length of the polymer or in terms of the physical space R is what determines the exponent nu. So if you like, nu is just really a way of translating from things that you have measured as a function of polymer number of monomers to physical space that you have occupied. So in the calculation that I did here, I was moving things in physical space, and hence the exponent nu appeared in some hidden way through the gammas. But when I'm doing the calculation, ultimately the answer depends on some entropy difference, which is really captured by the difference of the piece. Yes, they are if I did this calculation and I got my p's, these p's are like the etas over here. So then in order to translate the result of this calculation to a gamma exponent, I have to multiply by nu. You're right. Well, I mean, in some sense, there are all of these exponent relations. So if you like, A is more clearly related to the correlation exponents. And etas are correlation exponents. Yes. 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 Okay. So remember that I did this calculation for the polymer between two flat plates. And the answer was simply a product of a sine function and then some exponential that depended on n. So for getting the depletion, I could focus only on the sine function and not worry about the exponential that depends on n. So in that sense, I can sort of look at, forget about the n dependence, whatever it is, then I need the in the vicinity. Yeah, it cancels at the end, and essentially the depletion exponent tells me what is happening over here, and the endpoint of the polymer is way out there, so I don't really worry about it. Okay? But it's sort of good to ask these questions and get some kind of insight as to what all of this means. Right? But it's simple enough calculation. You can see what the reduction in entropy occurs, and polymers are really a wonderful way of thinking about reductions of entropy associated forces, what is universal, what is shape dependence, where is scale invariance come into play, and all of that. Anything else? Yes?
If you have multiple polymer strands, is it trivially...
For the case of these random walks that I have, if rather than having one polymer strand, I have F polymer strands, I simply multiply everything by F. If I have self-avoiding polymers, there is a very interesting epsilon expansion that you have to do, and you see that they get into each other ways, and the answer is not simply F, but it gets subtracted by F squared. Okay? What else did I want to say? I'm moving very rapidly. Soon I will have nothing to say. Okay, so maybe finish with the following story. Okay. So I said that all of these beautiful results were built on the fact that there was one and only one scale appearing in the problem, which was h. Now, the reason that I was able to do that was because I looked at the way that the surface was operating with the polymer as if there was no energetic cost of interaction between the polymer and the surface, and the ultimate object was what I would call the Dirichlet boundary condition, which was the z ended up being 0. At whatever boundary point that I had. Now, in the very first lecture, when I was constraining the field that I was calling phi, I said, well, there's potentially another boundary condition, which was the Neumann, where the derivative of z along some direction is 0. Okay? Now, clearly, in the space of all boundary conditions, these are not the only ones. I can write down a boundary condition of the form z of x plus some lambda dz by dx equals to 0 along some direction x. This has a name. It's called a Robin or mixed boundary condition. Okay. Now, such a boundary condition clearly introduces some kind of a length scale into the problem. Okay. And indeed, if you ask what does that mean, if I were to sort of look at something that satisfies this boundary condition, say along one direction, you would say that something like e to the minus lambda x, I guess x, let's call this c, x over c, would satisfy this boundary condition. Okay? So this C sets some characteristic landscape. And if I ask, well, what does this look like? It's a solution where as I go as a function of x, I have lots of things that are concentrated over a distance of the order of psi, and then this layer falls off, and then I practically have nothing. Now, can you think of a physical system where that happens? Sure. If you have a polymer that is attracted to a surface, the polymer that is attracted to a surface will form some kind of a layer to take advantage of the attraction to the surface, although by leaving space and coming here, you have lost a lot of entropy. The reason you do that is because you gain energy from being in contact with the surface. Okay? Fine. So what happens if I have a system that is energetically favored for the polymer to be attracted to the substrate? So at low temperatures, it is there. As I heat it up, it wants to have more entropy, so it starts to fluctuate more and more, and the thickness of this layer becomes larger, and there's typically a desorption transition above which the polymer says entropy is more important to me and goes into space. Okay? So as long as my boundary condition is of that form, I have an additional length scale C in the problem. I cannot use this kind of arguments that I was using before. But what about the point at which the desorption transition occurs? Where C goes to infinity. Right at that point, not above that point, right at that point, not below that point, there the boundary condition is that dz by dx equals to 0. So whereas the Dirichlet boundary condition is quite generic all I want to do is to impose the condition that the polymer doesn't go through things. The Neumann scale-free boundary condition is non-generic. I have to tune the system to be at the exact temperature where entropy and energy balance each other, and then the Neumann boundary condition holds. Okay? But once that holds, if I'm exactly at that point, then I'm again scale-free. Okay? So all of the arguments that I have over here will also be equally valid right at the transition point, except that now I will have a different A to calculate. Why do I have a different A to calculate? Because when I go through all of these calculations, I have a different boundary condition. Rather than psi equals to 0, I would have to put psi prime equals to 0. Okay? Actually, what is happening in the vicinity of this particular form is in some sense simpler than the case of the Dirichlet, because if I'm satisfying a condition where dz by dx has to be 0, then you know for sure that close enough z has to be roughly a constant. There can be no depletion, right? So that corresponds actually for p to p equals to 0. So I don't have to do any calculation for p when I'm at that transition point that corresponds to the Neumann boundary condition. Okay? Yes? Okay, I should really say in the normal direction, right? So if I have something like a shape, I would require the normal gradient to be 0. That's the typical Neumann boundary condition. But essentially, the conceptual part you can appreciate by the one-dimensional thing that I've written. Okay? So if p is 0, there's something in, yes? Okay, so the argument for what constitutes p was that on approaching the surface or the special point, this has to go to 0 with exponent p. So if if the gradient is constant, the value of the function is roughly a constant, right? And so that corresponds to p equals to 0, which actually gives you an interesting observation, which is that if you have a collection of objects, it turns out that the objects don't even need to be scale invariant. And you tune them to be precisely at this desorption transition for all of them, then they feel no force from the polymer, right? So essentially, the polymer moves around, and it is as if it is free space. It doesn't see the objects at all. There's clearly a loss of entropy because it cannot penetrate the objects, but there is some remnant of the attraction that it had that just makes up for that loss of entropy. For one object, yes. No, so the consequences of that is that for many objects, you have no forces. So there is an analogous thing that people work very hard for colloidal objects in a solution. In order for them to be no van der Waals attraction between them, you have to do an index matching so that the dielectric constant is exactly that of the colloidal particles or something like that. So if you like, this is some kind of an index matching where you have a solution of polymers and the objects experience no force because their temperature has been matched, the index has been matched so that you are precisely at this point. But you do get non-trivial results if you have, let's say, one of the objects to be at the Dirichlet boundary condition and the other object to be at the Neumann boundary condition. There is no reason why the two objects should have the same adsorption properties. And for these cases, then you have to calculate a different value for P when this transition occurs. The exponent that I calculated before is no longer valid, and you can do the corresponding calculations with these modified boundary conditions and see what happens. I still have 4 minutes, but I'm not going to launch into yet another topic. So you can ask me questions.
So for these many object case,
Yes.
the size of the object will be much bigger than any scale of the polymer, or otherwise can you get any?
No, the other way around. I need the polymer to be much larger. So essentially, I'm imagining really the calculation that I have done is that the one polymer is the medium that covers everything.
But can you then add a desorption transition for different objects or different shapes?
Yes, because, well, okay, so that is a finite size question. Whether if you have a sphere of radius r, the transition temperature is modified by order of 1 over r squared and things like that. Yes, that. Yes. Mm-hmm. Yes. Yeah. Yeah. Yeah, so some of the things that I mentioned about absence of scales, really I built the whole thing based on the assumption that I have scale-free objects, but then I introduce here multiple objects that are not even necessarily scale-free. So the precise statement is as follows. Suppose I have to solve this Laplacian of psi equals to d psi by dn in the limit of very large n, so I need to find the ground state of psi in the presence of these objects. Okay? Now, what is the boundary condition of psi in the presence of the object? It is that the gradient of psi should be 0. I claim that psi equals to a constant is a solution that satisfies that. That's it. Yeah, so that's the point, that only at that case I have the Neumann boundary condition. Yes.
Can you maybe repeat the motivation for the mixed boundary conditions or for the Neumann boundary condition?
Okay. So I'm in some sense working backwards. So I'm saying that somehow the space of all of the problems that we see are to be governed by some appropriate mathematics. And I know that among the various boundary conditions that I can write down to the lowest order that involve the function and its derivative, there is this boundary condition. I start mathematically with that boundary condition and ask what does that boundary condition correspond to physically. I say, oh, it corresponds physically to an exponential decay. And then I ask, among physical phenomena, do I know a case of the exponential decay? And I say that the absorbed layer has that character. So then I know I've sort of gone backwards. So now I know about the adsorption transition. I know the corresponding mathematics. In fact, if you did the absorption transition, you can figure out that this exactly is the correlation length, and you can even figure out what the critical exponent for the divergence of the correlation length is from this argument. Okay? Yeah. No. 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 So, yeah. So actually, all right. So this motivated us with the following. So we were hoping to find a corresponding indexed match condition for polymers that have self-avoidance. we found that the way to do that was to pattern the surface. So if you take a flat plate and sort of draw on it regions that are one boundary condition or another boundary condition, then you can achieve that. It's not as simple as this. There are additional length scale to worry about, but in principle, it can be done for self-avoiding polymers, yes.